Hey everybody, Trey here. Welcome back to another video. Today we're going to talk about a tornado setup that is one of my absolute favorites to chase, and that is the cold core tornado setup. You've probably heard the term cold core thrown around before in severe storms forecasting. We've used it plenty of times here on the channel in the past. These cold core setups are usually very efficient at producing tornadoes, but they're often overlooked because the parameter spaces associated with these setups are usually much more marginal looking than a typical plains or Midwest or Southeast severe weather setup. But you can see some very photogenic tornadoes and supercells in these cold core setups, and in this video we're going to discuss how to properly forecast these cold core setups and what you need to be looking for a textbook cold core tornado producing setup. So without further ado, let's get started here. First, we need to define what does cold core actually mean. And we're basically referring to the type of low pressure system that we're dealing with. And we can have a couple of different types here. We can have a warm core system, or we can have a cold core system. And the names are pretty self-explanatory. When we're dealing with a warm core system, we're dealing with a low pressure system that has lots of warm air at its center. And with a cold core system, lots of cold air aloft at the center of low pressure. So let's say we were an observer on the surface of the Earth looking directly ahead at a low pressure system. And so these blue lines I'm going to draw are the isobars, or lines of equal pressure. And let's say we could actually see them and make them out in the atmosphere as we're looking dead ahead at one of these low pressure systems. With a warm core system, it's going to be vertically stacked with height. So the center of low pressure is going to be aligned vertically as you go up in the atmosphere. So you can see here that the center of low pressure, these dips in the isobars here, are pretty much dead in the vertical here. And that's the main difference between a warm core and a cold core system. The most notable type of warm core system is a tropical cyclone or hurricane. As we know, it's a vertically stacked system with a very strong center of low pressure. In other words, the eye at the center of the low pressure system. Those are vertically stacked warm core systems. And with a cold core system, it is not vertically stacked. Instead, it's going to be tilted. The center of low pressure is going to be tilted with height. So if we were looking dead ahead at a cold core system, the isobars would look something like this. Again, the dip in the isobars is the center of low pressure. So you can see it's very much tilted off toward the west or northwest with height. That is the main difference between a cold core system. And cold core systems are generally the vast majority of systems, of low pressure systems that we see in the U.S., what we call mid-latitude cyclones that help produce severe weather in the U.S. Those are going to be cold core systems. We're talking about a specific type of cold core system. We're looking at mainly those that are closed at 500 millibars, so a closed cold core 500 millibar low. So what that means is that we're going to look at the height contours here. This is an example, and you'll notice that the height contours here are closed off surrounding the center of circulation here. That's typically what we're going to be looking at with a cold core tornado setup, is these closed 500 millibar lows. And you can see also here that there's very strong cold air aloft. These dashed red lines are the temperature contours, or isotherms. So we're looking at about minus 19 or minus 20 degrees Celsius here at the core of the system there. And I've seen cold core systems with minus 20, minus 22, 24 degrees Celsius air at the center of the circulation at 500 millibars. That's very, very cold air aloft. And that's what mainly drives these systems. These systems, unlike a typical sort of plains or Midwest or Southeast severe weather setup, are very much driven by thermodynamics versus kinematics. Now, what do I mean by that? Well, usually in a typical severe weather setup in the plains or Southeast or Midwest, you have very strong wind shear in the atmosphere, very strong kinematics in the atmosphere. And that wind shear, of course, there's adequate instability available, but that strong wind shear helps to allow storms that go up in that environment to rotate and become supercells and eventually produce tornadoes with strong low-level shear. So those are mainly kinematically driven setups. That's not going to be the case with cold core setups. They're going to be more driven by thermodynamics. That cold air aloft really helps to rapidly destabilize the atmosphere because the main area of interest is going to be tucked right up underneath that cold pocket of air aloft. And we'll discuss the main parameter spaces that we'll see with cold core setups in a second and why that's the case. But you can see how that area of interest is well removed from the strongest area of winds aloft. So it's going to be well removed from the area of strongest wind shear aloft. So you're not going to see those large clockwise looping hodographs that you'd often see with a typical severe weather setup. The overall wind shear is going to be much more marginal in these setups. But there's going to be adequate shear, especially in the low levels, and that cold pocket aloft really helps to rapidly destabilize the atmosphere and help to stretch any sort of spin there is in the low levels and stretch that very efficiently into the vertical to become a tornadic circulation if a supercell passes over that area of spin. So that's the main difference between a cold core setup and a kind of typical severe weather setup. It's that it's very much thermodynamically driven based on that very cold air aloft helping to destabilize the atmosphere and help stretch that low-level shear, whatever low-level shear there is, into the vertical to become a tornadic circulation. So let's kind of expand on the type of parameter space that we're likely to see with a cold core tornado setup. Now, we said that these are thermodynamically driven setups, but when we look at the kind of quantity or the actual value of CAPE, mixed layer CAPE, our measure of instability, it's not usually going to be that large. So we're usually going to see low instability or low CAPE in these setups, and that is due to generally a low amount of low-level moisture. Generally, I've seen cold core setups with dew points at the surface as low as the low to mid 40s. And if you were to look at that at first glance, you might think, well, we're not going to see severe weather at all with 40-degree dew points. The low levels are not moist enough. But that's not usually the case. Again, because that cold air aloft is so potent and helps to rapidly destabilize the atmosphere, that can help compensate for that low sort of overall instability in the atmosphere and that low moisture quality at the surface. The thing about cold core setups, though, is that even though the value of the CAPE might be small, it's usually generally confined to the lowest few kilometers of the atmosphere. So as we've talked about before, the 0 to 3 kilometer CAPE, or 3 CAPE, and we've done a video about that in the past few weeks, and I'll put a link to that as well in the description box below. The 3 CAPE is usually very high in these setups. So the instability is very much concentrated in the lowest levels of the atmosphere. And so that's what helps really stretch that spin, whatever spin there is near the surface, into the vertical. It's because we have that very high 3 CAPE, or that CAPE is very concentrated in the lowest levels of the atmosphere. Generally, with a cold core setup, we're dealing with low wind shear as well. Because, as we stated before, let's go back to our example here. Our area of interest is up underneath that cold pocket of air aloft. Again, it's well removed from the strongest flow aloft and the strongest low-level jet. Those winds just above, about a kilometer above the surface that we usually see in pretty significant tornado events. It's going to be well removed from that. And again, but usually it's going to be adequate low-level shear and deep layer shear for supercells, adequate, maybe even marginal low-level shear for tornadoes. But again, that instability concentrated in the lowest levels of the atmosphere helps to stretch whatever spin there is, however marginal it is, into the vertical, and you can get tornadoes even though the low-level wind shear is pretty meager to begin with. So I want to draw your attention here to a couple of journal articles here. This first one here is from 2006 by a meteorologist whose name is John Davies. He is a well-known private meteorologist out of Kansas City. He's kind of the foremost expert on these cold core 500 millibar low tornado setups. And this is kind of the foundational paper on these cold core type setups here. I'm going to put a link to this paper in the description if you want to read more about these type setups. But he really was the first one to really go in depth with these cold core tornado setups and look at the actual kind of parameter space and the ingredients that are needed for these events. Here's another one that John Davies did with SPC forecaster Davies Guyer on these cold core 500 millibar low tornado events. And I want to draw your attention here to figure 1 in this article. So zoom in here on this figure. And these are a couple of composite diagrams showing the general surface features that you'd expect that increase the likelihood of a cold core tornado event. So let's start with the one here on the left. So generally in both of these cases, we're looking at a 500 millibar closed low. The center of circulation is in very close proximity to the surface low. generally less than 200 miles or so. Now, that's just kind of a general rule of thumb. I've seen some cold core or pseudo cold core setups that don't really follow this rule, and we'll talk about that, an example of that at the end of this video. But generally, this surface low is going to be kind of tucked underneath that cold pocket aloft, very close to the center of the 500 millibar circulation. General rule of thumb, within about 200 miles. We have our cold front here extending up into the surface low, some portion of an occluded front there leading up into the surface low where the cold front has caught up to that warm front, and the intersection of that kind of warm front with the cold front, kind of that triple point there, just to the east or northeast of the surface low there in this green oval, is where you're most likely to see tornadoes. Our warm sector here, characterized with moisture kind of feeding up in a tongue up into that sort of triple point area. Anywhere from mid to upper 40s to low 50s dew points is generally the case with these cold core setups. And that is one type of kind of schematic diagram of the features that you might see with the cold core setup. This one here on the right is a little bit different, but the exact same idea here. We have the cold front trailing back here along, well back to the west, and we have kind of a dry line feature out here leading up into the surface low, with our warm sector up in here, dew points, low to mid 50s dew points leading up into the surface low there to the south of the warm front, and right at that triple point, that boundary between the dry line, that moisture axis, and the warm frontal zone, right up in that surface low is where we're most likely to see tornado formation with these cold core setups. So this is a diagram, a couple of diagrams I often go back to when I'm forecasting these cold core setups to see if a setup kind of fits the bill. I want to draw your attention also to table 1 here, and this just shows, this is a comparison between cold core tornado events here in this top row, or this middle row here, and typical supercell tornado events here. And these are a bunch of different parameters that we often use to forecast these events. And I want you to focus on these bolded values here. These are the median values of each of these parameters here. And we'll look at these few right in here. These are kind of the most important ones I want to take note of. Notice that the mixed layer CAPE here is much less with cold core tornado events than it is with typical supercell events. Median value of just under 800 joules per kilogram mixed layer CAPE there with cold core events. Almost 1,000 joules per kilogram less of a median value for a typical supercell tornado event. So you can see here that the overall instability is much, much less with these cold core tornado events than it is with a typical supercell tornado event. But here is the kicker, the 0 to 3 kilometer CAPE or 3 CAPE. Notice that it is much higher with the cold core tornado events than the typical supercell tornado events. Again, both of these, 3 CAPE is a parameter that is very much a discriminator between tornadic and non-tornadic events in any situation. But notice here that with cold core events, it tends to be a little bit higher than with our typical supercell events. Also notice here that our shear, both in deep layer shear here, 0 to 6 kilometer shear, and our 0 to 1 kilometer shear, our low level shear, is much, much less in these cold core events than it is with the typical supercell tornado events. Notice our 0 to 1 helicity as well, low level storm relative helicity, is much less, almost 100 meters squared per second squared less in these cold core events than typical supercell events. So this just helps to confirm the fact that these cold core events are generally low CAPE, low shear type events, but adequate shear. But because that 3 CAPE is often much, much stronger, that low-level instability really helps to stretch whatever low-level shear, what low-level spin there is into the vertical to help produce tornadic supercells. All right, let's go ahead and look at some examples there. We've gone through what we tend to look for in different events, cold core events. And so let's go ahead and go through some examples. So this first one here is from May 21st, 2019. If you recall that date, May 20th, 2019 was that high risk in the for southwest Oklahoma into the southern Texas Panhandle, northwest Texas area, produced the Mangum, Oklahoma tornado. It was the very next day. The trough moved off toward the east, and you can see here what we're dealing with. Very much a closed circulation at 500 millibars here. This is at 21Z, 4 p.m. You can see closed contour there as the low kind of jets off, ejects toward the northeast there. Closed contour there. pocket of cold air aloft. Here you can see, if you can make out that number, it's minus 22 degrees Celsius here. So very cold air aloft associated with the center of this system here, overspreading much of Kansas throughout the day. See the main jet streak here off toward the east, across kind of the Kansas-Missouri border region. That cold pocket aloft is placed just off to the west there. Let's go on to our surface pattern here. We'll go forward in time. Very strong surface low here, 992 millibar low, centered over kind of west central Kansas there. And notice our setup. Surface low very much tucked underneath that cold pocket of air aloft. We'll go 500 millibars here to our surface low. Very much checking the box for that close proximity of the surface low to the center of the 500 millibar low. We'll look at our moisture here, go forward in time, and you can see that we have a nice moisture tongue spreading up into that surface low up there into northwest to west central Kansas there. These dashed blue lines are the dew points here, so you can see dew points. The shaded blue contour is above 56 degrees, and we go decrease with northwest extent here, 52 degree dew point line there, right in there. So modest dew points at first glance, 52 to 55 degrees, generally modest for a typical severe weather event. Let's look at our 0 to 3 kilometer cape, though, and you can see with time that it really, really increases there. Bullseye of 150 joules per kilogram there of 3 cape there, coincident with some of that surface vorticity up into that surface low where winds are most backed out of the southeast. So let's take a look at a proximity sounding here. This is from Salina at 21Z. And notice this is just a classic cold core profile. You can see the instability here. Cuts off here below 300 millibars. So these storms are very, very low topped supercells that we're going to fire. You can see all of that cape is really concentrated here in the lowest levels of the atmosphere. 0 to 3 kilometer cape, 230. That is outrageous 3 cape. So any spin, any low-level spin was going to be stretched into the vertical very, very efficiently to produce tornadoes with supercells that fired. And you can see here the wind profile did favor supercells here. You can see some curvature in the low levels there. And this is often what we see with these cold core setups. And we've done this kind of exercise before where the hodograph is used to kind of as a proxy to the construction of the supercell and how the precipitation is vented off with height. And you can see here that this would be our low-level hook, and then our precipitation would be vented off well toward the north with a storm motion this way. So this would produce any tornadoes that would be produced would be very photogenic, very clear of precipitation. And that is generally the case with these cold core setups. You'll often see bright blue skies and these low-topped cumulonimbus clouds, these supercell storms, and very visible areas of mesocyclone and tornado activity on the southern flank. So this is our satellite image, classic sort of satellite image here as we go through the day. Oftentimes with these cold core systems as well, you'll see a lot of morning showers and storms, but as soon as they move off, you get very rapid clearing in the afternoon hours. You can see here that those storms move off rapidly in the afternoon. We get lots of surface heating here to really help couple with that cold air aloft to really destabilize the atmosphere here. Notice in the sounding we do have almost about 1,500 joules per kilogram of cape, which is very much on the high end for these cold core tornado events. So you can see rapid destabilization. We get storms to fire here, kind of in an arc there out ahead of the surface low. We'll look at our radar here. You can see those early showers and storms move off toward the east, and then we go with time and we get kind of scattered supercell development here, kind of in an arc. You'll generally see that the storms, your surface low will be back in here, and you'll get an arc of supercells to fire just out ahead of it, right where those boundaries kind of intersect. That moisture axis here leading up into the low, and kind of that tongue of moisture there, kind of the warm front leading up into the low, and that's where your most likely zone for tornadoes is going to be, right at the kind of the apex of that arc there. And we had a number of tornado reports on this day. You can see the bulk of the tornado reports right there, where all the favorable ingredients intersected just ahead of that surface low. Here's an example of one of the tornadoes here near Seneca and Oneida, Kansas. You can see very photogenic tornado, no precipitation around it at all, as all of that precipitation was vented off toward the north away from the mesocyclone based on that wind profile aloft. So pretty classic cold core tornado event there. Let's go ahead and look at another one. This is a little bit more marginal. This is one that I actually chased here. This was near a tornado that occurred near Olathe, Kansas, near Kansas City, on March 15th, 2021. So we'll go through time here and look at our 500 millibar pattern. So you can see closed circulation here at 500 millibars. Lots of cold air aloft, minus 26 degrees Celsius air at the center of this 500 millibar low. That's very, very cold air aloft. So that was going to really help to destabilize the atmosphere once the early storms moved off. And we'll take a look at that in a second. So boxes checked there for our 500 millibar low. Here's our surface pattern. You can see the surface low moves off toward the east pretty rapidly. Surface low located very close to that center of circulation aloft. You can see the cold pocket aloft is right above that surface low there. So boxes checked for the surface low and 500 millibar low centers in proximity to one another there on this day. Moisture was much more marginal on this day, but you can see the blue contours here. This is 44 degrees dew point contour here. You can see that, but you can see marginal dew points feeding up into that surface low and kind of that tongue there right along the warm frontal zone, which was draped somewhere kind of right in here. You can see the wind shift there and the pressure tongue there. So very meager moisture here, mid 40s dew points. So again, at first glance, you'd think, well, this is not going to be a severe weather setup. But let's look at the 0-3 kilometer cape here as we go through with time. 21Z here, bullseye of 3 Cape just south of Kansas City with some attendant surface vorticity, surface spin as well. Here's a proximity sounding from just south of Olathe, south of Kansas City there on this day. Modest cape here. This is much more classic cold core type thermodynamic profile, just about 500 joules per kilogram of mixed layer cape there. But notice the 3 Cape, just over 100 joules per kilogram there. So most of that cape was concentrated there in the lowest levels. And you can see here the tops of the storms barely above 500 millibars there. So very, very low top storms, which is usually the case with these cold core events. Photograph not super favorable for tornadoes, you might think. And it was kind of difficult to get a proximity sounding right along that warm front. But I do believe that these photographs were a little bit more enhanced there as far as low-level shear goes, right along that warm front, which is where the Olathe tornado occurred. But enough low-level shear to get stretched into the vertical, and any spin, any vorticity along that front was going to get stretched into the vertical with fairly moderate sort of low-level instability there. And so here's our satellite view. You can see clouds early on here. We're focusing right in this area. Clouds early on, cleared out. We got several supercells to fire, kind of scattered supercells to fire within that cumulus field as the clouds moved off, and that is what produced the tornadoes. We'll go with our radar here, so you can see, remember where our surface low was, kind of a little bit elongated right in here, and storms firing right at the tip of that moisture tongue, right along the warm front there, leading up into the surface low just south of the Kansas City area. And these went on to produce tornadoes, a couple of these little beans there. One of those produced the Olathe tornado. So you can see where the tornado reports are, right at that 3 Cape and surface vorticity bullseye, right just ahead of that surface low there. Just to give you a little snapshot of what it looked like there. It was a nice kind of cone tornado, not fully condensed, but was able to get pretty close to it. And it was able to, it was flinging a lot of debris everywhere, lots of leaves. But it was a fairly weak tornado, but a tornado nonetheless, and a good example of a marginal-looking environment that was really assisted by that cold air aloft from that cold core 500 millibar low. A few more examples here, a couple more examples. So this was from January 30th, 2021. This was a wintertime setup. And you can see a very potent trough here, move off toward the east. Notice that this one is not quite closed off. So you can have some of these setups, these cold core setups, that don't perfectly follow that schematic diagram we looked at earlier on from Guyer and Davies. It doesn't have to be perfectly closed off here. We don't have a closed contour here at 500 millibars, but we have a potent trough and a very cold pocket of air aloft. You can see here minus 22, 24 degree air here right at the center of this trough. The base of the trough moving through southern Oklahoma, that jet streak there. So the cold pocket aloft right over northern Oklahoma, southern Kansas there throughout that day. We'll look at our surface map here. Surface low moving off toward the east as well. And once again, just a classic setup here. Surface low right there in southeast Kansas with our 500 millibar trough, that cold pocket of air aloft, pretty much coincident with that surface low there. So we check that box. Surface dew points here once again on the marginal side, but notice those dashed blue lines feeding up in a very pronounced moisture tongue right up into that surface low, which is located right in there. And again, dew points, this is the 48 degree dew point contour there. So, mid to upper 40s dew points there for this setup. Doesn't have to be lots of moisture for these setups. That cold air aloft really helps to compensate for the lack of low-level moisture and instability. So once again here, we'll look at our 3 cape, and that's about as textbook of a bullseye as it gets right in there. Bullseye right in there, some surface vorticity as well. This, if you just were to look at that map and look at these few maps, you know that this was a very textbook cold core event with that 3 cape bullseye there. Proximity sounding from Tulsa, just to the south of the area of interest here. Once again, very low top storms, that equilibrium level, that top of the storm, very, very low top storms here. But notice that we have a nice fat cape there in the lowest levels. Only 673 joules per kilogram of mixed layer cape, but our 3 cape, 140 joules per kilogram. So all of that instability concentrated in the lowest levels. Very favorable hodograph here. Lots of low-level shear, lots of low-level vorticity there that was going to be very efficiently stretched into the vertical and into a tornadic circulation there. Here's our satellite image. Early morning storms move off. We get nice clearing throughout the afternoon, and it only takes a couple of hours with these cold core events because the air loft is so cold and the surface heating is usually so strong after the morning storms move off that you get really, really rapid destabilization. So, usually we don't like to see morning convection with a typical setup, as that kind of ruins the instability for later on in the event. But with these setups, these cold core setups, it only takes a couple of hours to destabilize the atmosphere. So, and this was one of those cases. Very strong surface heating here, cold air aloft. And we got storms to fire here just kind of on the Kansas-Oklahoma border up there, right ahead of that surface low in southeast Kansas. Let's look at our radar here. Morning storms quickly move off, and we get storms to fire right out ahead that produced a couple of tornadoes up here in far northeast Oklahoma, just south of the Kansas border. You can see where the tornado reports are there near the town of Wan, Oklahoma there. Well, there's a picture of that tornado there. So even in January, cold core setups often produce. Now this last one here, this is the Winterset, Iowa case, the infamous Winterset, Iowa tornado event from March 5th, 2022. This was not a true cold core event, but this was kind of what I called a pseudo-cold-core event in my forecast discussion for this day. And that's because it had some characteristics of both a kind of typical setup and a cold core setup as well. So let's go through here, 500 millibars. Once again, you'll notice that we don't really have a closed center of circulation here. Maybe you could argue that we do close off a little bit in here. But generally, this was kind of an open wave. But notice, again, very strong cold pocket aloft, minus 22 degree air here at the center of this trough. But you'll notice our area of interest is still kind of under that cold pocket aloft, as well as that area of strong winds aloft. So the wind shear with this event was much stronger than what we typically see with a cold core event, because it was just kind of in that western extent of the jet streak, that area of strong winds aloft. Let's look at our surface low here. We had a surface low rapidly translating to the northeast out ahead of the 500 millibar trough. Whoops, let me go back here, go to the pen. So yep, here's our surface low here, a little bit elongated, but still very, very close, in close proximity under that cold pocket aloft there at the 500 millibar trough. Let's look at our dew points here. Very classic moisture tongue here. This one had a little bit stronger, a little bit better moisture quality than some of the previous events we've looked at, but nice moisture tongue feeding up into the surface low there. Dew points in the approaching the upper 50s here across southwest Iowa. So this was definitely a higher end case that kind of was a hybrid between a true cold core event and a typical supercell tornado event. Let's look at our 3 cape. And you can see bullseye there across southwest Iowa with lots of surface vorticity right ahead of that surface low where the winds were most backed out of the southeast. Here's a proximity sounding here. Once again, a little bit more instability, a little bit more of a typical supercell event characteristic to this event. So a little bit taller storms here, a little bit more robust convection here, but marginal instability, just about 1,000 joules per kilogram of CAPE there at Des Moines. That may have been a little bit underdone, but 3 CAPE approaching 100 joules per kilogram there, so decent 3 CAPE in the low levels, right at that bullseye. But you can see the low level shear and the deep layer shear was pretty strong, much stronger than what we usually see from a cold core event. 0 to 6 kilometer shear of 75 knots there, so plenty of shear for supercells and lots of low level shear just ahead of that surface low for tornadic activity. Our satellite image, this was a textbook evolution. Morning storms move off. We get a couple hours of destabilization and then rapid supercell development there, thanks to that quick destabilization from the cold air aloft and the surface heating behind that early wave of storms. And your supercells, the Winterset storm was right in there, producing a violent tornado at this time. So here's our radar. Once again, early storms, we'll go back. Early storms move off, and we get a nice, this was a classic sort of arc of supercells to fire right out ahead of the surface low, where winds are most backed out of the southeast. So the tornado threat with these storms was the highest here, right at the apex of that arc. We move on with time, and we got the Winterset storm there, which produced a violent EF4 tornado. And you can see there all the tornado reports right ahead of that surface low in that under that cold pocket aloft. And of course, we know that it was a pretty massive tornado, was rated EF4 there. So it doesn't have to be a textbook, follow that schematic diagram exactly. But certain events can have characteristics of cold core events. And when you have a profile like that with strong low-level shear, strong low-level instability, you're likely to see some good tornadic activity with that. So that's going to do it here for this video. I hope you learned some stuff about cold core events. Once again, copy and paste these diagrams here. These are always good go-tos here from that Guyer and Davies article. Once again, I'll post the links to both of these articles in the description below, as well as the video that I did on 0 to 3 kilometer CAPE. But copy and paste this diagram here and definitely use it when you're forecasting cold core tornado events. Again, these are some of my favorite events to chase because they're such efficient tornado producers when the ingredients come together. So with that, that'll do it. Thanks for watching, and we will see you in the next video.